Hello, everyone. Welcome to the OC3 webinar of July. Today, we are very glad to have our Professor Lorraine Lisiecki from University of California, Santa Barbara as our speaker. First, I will very briefly introduce Lorraine. Lorraine got her bachelor and master degree from EPS department, MIT. After that, she went to Brown University and got her PhD there. She then did her postdoc at Boston University before she started her faculty position at UC Santa Barbara. Her research focuses on computational approaches to the comparison and interpretation of paleoclimate records. She's particularly interested in the evolution of Pliocene to Pleistocene climate as it relates to orbital forcing, glacial cycles, the carbon cycle and deep ocean circulation, and in improving paleoclimate age models and quantifying uncertainty. Today, she will talk about a multi-proxy approach to construct regional age models. Okay, with that, let's welcome Professor Lorraine Lisiecki again. Lorraine, please start your talk. Thank you very much.
Sure, thank you, Ning. And I want to start by thanking OC3 for inviting me to speak today, and for all of you for coming to hear about this new age modeling software that we've been developing. So it's been a group effort. The PIs on the project are myself, Jake Gebbe from Woods Hole, and Chip Lawrence, who's an applied mathematician from Brown. But the bulk of this work has been done by Tae-Hee Lee, who is Chip's former student and now a postdoc at Harvard, and my student, Devin Rand, who'll be getting his PhD next year. So most of the hard work was done by those two. What I want to talk to you today about is some new software that we've developed called BIGMACS, which is a Bayesian technique for estimating age models using multiple kinds of age proxies. And it's really designed to develop age models that are regional or local to help deal with the fact that Benthic 018 changes are not synchronous globally. So what we mean by multi-proxy age models is we're talking about two different kinds of age information. One we're calling direct age proxies, and so these would be primarily radiocarbon dates, but also dated tephra layers or even tie points to well-dated records like ice cores or speleothems. And then the other type of age information are relative ages from stratigraphic alignment. So in this case, we're going to be looking exclusively at Benthic 018 alignment proxies, although some tentative work that we've done on the software suggests that it may work for planktonic alignment as well. So just as an illustration, here are 4 semi-random cores that have both Benthic 018 and radiocarbon dates. The location of the radiocarbon dates are marked with the triangles here. And so if you were to develop an age model using radiocarbon alone for any of these cores, the resolution of the age constraints is not as good as the Benthic 018 resolution and doesn't extend over the entire length of any of these individual records. But if we develop a multi-proxy age model, we can use both the Benthic 018 alignment and the radiocarbon dates to develop well-constrained ages for these cores over the entire over most of the time span for each of these records, and take advantage of the radiocarbon dates from all of the cores together. So that's sort of where we're working towards. So, and we've got a lot of ground to cover in this talk. So here's sort of an outline of the order we're going to go through things. I'm going to give a little bit of background on some existing software for radiocarbon age models and Benthic 018 alignment. There's a lot of different packages out there, so this isn't an exhaustive list. Then I'm going to talk about the methods that we use in this new software, BIGMACS. First, talking about the model that we use for sedimentation rate variability, and then the Bayesian framework we use for developing the multi-proxy age models. Then we'll look at some of the results from BIGMACS. We'll compare, you can run BIGMACS in 3 different modes: radiocarbon only, 018 alignment only, or multi-proxy mode. So first we'll look at just the radiocarbon only age models compared to some existing software. And then we'll compare the multi-proxy age models to the radiocarbon only age models to look at the advantages that we get from combining both sources of information. And then finally, BIGMACS also creates stacks. And so we'll take a look at the stacking procedure that BIGMACS uses compared to existing stacking techniques. And we'll look at some example stacks that we've constructed with BIGMACS. And then I'll end by summarizing some of the advantages and limitations of the BIGMACS software. So we expect that this will be submitted to Climate of the Past within the next 2 weeks. We're just about ready to submit on this manuscript. So to begin with, let's look at how radiocarbon age models are constructed. So going from the radiocarbon measurements themselves, we have to calibrate to calendar years, and that has some uncertainty from the calibration curve. We also have to take into account the reservoir ages of the surface water where the radiocarbon samples are coming from. And so and the measurement uncertainty itself. So we have multiple sources of uncertainty for the radiocarbon, but we also have uncertainty. We want to estimate ages throughout the core, not just at the points of the radiocarbon dates. And so we also have uncertainty for ages estimated between the radiocarbon dates. And so, for example, you can see that away from where the sediment has been dated directly, we have larger uncertainties. And that's because the sedimentation rate can be changing between those dates. And so the amount of age uncertainty increase that you get between radiocarbon dates depends on what assumptions you make about the sedimentation rate variability within the core. So here's an example of Bacon, the output that you get if you run Bacon to develop a radiocarbon age model. And at the top, in the middle and on the right, those are the models of sedimentation rate variability that Bacon is using. So in the center panel is just what is the frequency or the probability of any given sedimentation rate. Bacon uses the inverse of sedimentation rate, so it's actually years per centimeter, but we can think of that, pretend like we're looking at the inverse of sedimentation rate. And then on the right is the memory of the sedimentation rate. So that is how rapidly does it change? Does it change sluggishly, or can it switch back and forth between high and low rates very quickly? And so the green curves in both of those panels are the prior estimates. So that's the information that Bacon starts with for what the sedimentation rate model is. And then the gray curves are the posterior. So those are adjustments to the model based on the character of the data that you have given the software. And so Bacon will start out with a guess on what the shapes of those curves should be. But oftentimes, in order to get a good fit with the radiocarbon dates, you have to make some adjustments to those prior estimates to get a curve that passes through the radiocarbon dates the way we expect it should. And so there's 2 parameters to adjust for the sedimentation rate frequency model and 2 parameters to adjust for the sedimentation rate memory. And a lot of times people who are running this don't have a specific knowledge about the kinds of sedimentation rate changes at their location and how they would translate into specific parameter values. So a lot of times it's sort of a trial and error and then subjectively choosing the model that looks right to people. And there are even more things that you can adjust as well, like the number of intervals that the sediment core gets divided into. And so this can be kind of a time-consuming process. And ultimately, a lot of times the result is just the one that the user thinks looks good. And so there's another software package that's been developed recently called Undatable that sort of emulates the kinds of results you get from Bacon and some of these other more sophisticated radiocarbon age modeling software, where instead of having lots of parameters to tune to adjust the sedimentation rate model, they've simplified it down to 2 parameters. It's not actually physically modeling sedimentation rate, but produces similar results. And so one of those parameters is X factor, and that just controls how large the uncertainties grow between the radiocarbon dates. And then the other one is boot PC, which is a bootstrapping technique that says how many radiocarbon dates are we going to classify as outliers, and affecting which dates get classified as reversals as well. So that's just 2 knobs. And again, it's a subjective exercise, but it reduces the amount of time needed to explore the possible solutions that you could evaluate. So our goals for this new software is we want to provide a realistic sedimentation rate model for ocean sediment cores that eliminates the need to do this tuning and makes the results less subjective because it's actually based on the amount of sedimentation rate observed in ocean sediment cores. And then the second goal that I started out with is that it's multi-proxy, so that in addition to radiocarbon dates, we're going to use Benthic 018 alignments to constrain ages between and beyond the radiocarbon dates. And that should improve the accuracy, reduce the uncertainty between the observed radiocarbon dates. So now I want to talk a little bit about Benthic 018 alignment, which is the other part of this BIGMACS software. So when we align Benthic 018 signals, we're assuming that we have the same Benthic 018 change at the different sites that we're looking at, and that change is synchronous. Now, it's not always a perfect assumption, but that's the whole philosophy behind Benthic 018 alignment, is that you've got the same signal recorded in multiple locations. And so in order to evaluate an alignment, the primary thing that you want to do is minimize the amount of misfit between the 018 curves. So here we've got a blue record and a purple record, and we're going to assume this is a signal that is a real climate signal recorded in both locations. And we want to adjust the age model of the blue one to fit the purple one. And then we're evaluating the residuals and 018 values between the curves. So the first thing we could do is shift the ages younger or older in the blue curve to try to improve the fit. The other thing we can do is stretch or squeeze different parts of the records. So when doing that stretching or squeezing of the blue curve, what we're doing is simulating the effects of sedimentation rate change. So in addition to fitting the 018 record, we also want to be realistic about the amount of stretching and squeezing that we do to help ensure that we haven't misaligned any of the features. So generally, we're going to prefer age models with less sedimentation rate change. So here we see the common theme of sedimentation rate variability that affects both 018 alignment and radiocarbon. And then in order to do these alignments, what you do is you consider all possible alignments of the blue curve to the purple curve and evaluate the fit both with respect to the 018 residuals and the amount of sedimentation rate variability. And you find a curve that passes through the minimum penalty score for those alignments. So moving on to look at how we can better characterize sedimentation rate variability. So in the original 018 alignment software that I did called Match in 2002, it's just uses parameter tuning in order to limit sedimentation rate variability. So in 2014, we came up with a probabilistic version of that software called HMM Match that used a model of sedimentation rate variability based on 37 different radiocarbon dated cores with high resolution radiocarbon dating and excluding cores north of 40 north so that we're not so much worried about the effect of reservoir age changes for this. So these are the 37 cores and their estimated sedimentation rate variability from the radiocarbon dates. And they've all been normalized, which means we've divided by the average sedimentation rate in the core. So 1 is the average sedimentation rate, and then we're just looking at the factor by which the rate has increased or decreased in different parts of the core. So using that data, we have a model of the sedimentation rate variability, the frequency of high or low sedimentation rates from that set of cores. And so that's what you see in the histogram here, and we fit a mixed log normal model to describe the shape of that curve. So that gives us a physically based model for sedimentation rate variability. And additionally, we need a memory component similar to Bacon that says, how frequently do we expect those sedimentation rates to change in the core? And so we use a transition probability matrix where we evaluate the frequency at which the core expands, transitions between three different states. One is just near the average. One is expansion, or where you have to stretch the curve because the sedimentation rate is low. And the other is contraction, where you're compressing the curve to make it fit because the sedimentation rate is high. So we're looking at how frequently the sedimentation rate goes from being high to low to average between those three states. So this is an example output from HMM Match. It's designed to do these orbital scale alignments. In addition to the original publication of HMM Match in 2014, we also did a paper by On et al., where we created a new stack for the Pliocene-Pleistocene. So it works for these longer timescales for HMM Match. And this is just an example output where we have one record aligned to the LRO4 core. We can look at the sedimentation rate changes. These are probabilistic models. So what I'm showing here is actually just the median age model for the result. And the sedimentation rate changes that would be associated with the median age model. But you actually get several hundred or 1,000 different samples of age models for different ways to align that core to the target. And that lets you generate alignment uncertainty estimates, so a 95% confidence interval window of the aligned ages, which you see plotted here at the bottom. And for these orbital scale records, the age models are typically plus or minus 2,000 or 3,000 years, but there are some areas where the alignment uncertainty is larger, as you can see from the bottom curve. One of the shortcomings with HMM Match, though, is it only does O18 alignment. There's no way to provide any additional age constraints probabilistically into that alignment curve. And so that's one of the things that we're tackling with BIGMACS, is adding in this component of additional age constraints. So the reason we call it BIGMACS is it's an acronym for Bayesian Inference Gaussian Process, Multiproxy Alignment of Continuous Signals. And at the bottom, you can see the Bayes equation that we use for BIGMACS. So I'm going to take you through the components of that. On the right is the probability of an age model given our sedimentation rate parameters that we've estimated based on sediment core data. So this is the probability of a given set of sedimentation rate changes, regardless of what the data are in the core. The component that you see here in the middle is the probability of the residuals or misfit in the radiocarbon and O18 data, given the age model and the data that's present in that core. So we have generalized students' T distributions to estimate the amount of misfit we might expect relative to the radiocarbon dates, as well as between the O18 records and the alignment target. And what you see there at the bottom, those gray bars are actual O18 residual data from some of the cores that we've been working with. And then you combine those two sources of information together to estimate the probability for any given age model with respect to the data and the parameters. And so you generate sample age models sampled in proportion to their probabilities. The black bars are the radiocarbon dates for that core. You can see the thin gray lines are the sample age models that have been drawn. You have a median age model drawn through that, as well as the 95% confidence interval bounds. So those are the kind of results that you get from BIGMACS for aligning a particular core. So some of the advantages of BIGMACS is that it doesn't require parameter tuning. So we've looked at least 50 different cores so far, and we're generating robust results without having to tune the parameters because we're using this model of sedimentation rate variability that's realistic for ocean sediment core data. Now, it doesn't mean there aren't some ocean sediment cores that are particularly unusual, where the defaults might not work, but it's quite robust for a wide variety of cores that we've looked at. And so now I want to give you a comparison for one particular core to compare what you'd get with Bacon or Undatable compared to, and here we're just looking at the radiocarbon only age model for BIGMACS. So on the left here is a Bacon age model using the default parameter settings. And what you can see for this core, Bacon has estimated relatively steady sedimentation rates that don't very closely follow through those radiocarbon dates. In comparison, Undatable really closely follows all of those radiocarbon dates so that it gets very large sedimentation rate changes there in the middle where there's a cluster of radiocarbon dates, whereas Bacon just sort of passes through the middle of that cluster. So if we look at what BIGMACS does, where we've actually put in a model of ocean sediment core data variability, is that it's more similar to Undatable, but not quite as extreme as the sedimentation rate variability in that center panel. And it's passing through the radiocarbon dates, although some of them it's kind of on the edge of that 95% confidence interval. Another thing that you often see with Bacon is that sometimes it doesn't pass through the last radiocarbon date, and that has, I think, to do with not starting with a good estimate of average sedimentation rate. And so BIGMACS does a much better job of passing through the beginning and end radiocarbon dates. So that's what we can do with BIGMACS with radiocarbon only and no parameter tuning. Additionally, because we can run it in multi-proxy mode, we can reduce age uncertainties by providing additional constraints from the Benthic O18 alignment. And when we run it in stacking mode, we can leverage radiocarbon dates from multiple cores simultaneously. So beginning with just the alignment, and we'll look at the stacking later, by using two different kinds of age proxies, we can reduce our age uncertainty estimates. So here we're looking at aligning one particular core off the west coast of Africa to a stack. I will show you the generation of that stack a little bit later in the talk. But the purple and blue dots there are the Benthic O18 data aligned to that stack, which is shown in gray. The purple points are the estimated ages of the O18 using O18 alignment only, and the blue are our multi-proxy alignments. And so you can see that the multi-proxy age model is a little bit different from the O18 only. There's some offset between the blue and the purple points. And in particular, the Holocene is a tricky part of the curve to align using O18 only because it's very flat. And so you can shift the age model quite a bit without affecting the misfit between the O18 data very much. However, when we run it in multi-proxy mode, we get some extra age constraints that help improve our Holocene dates. So the purple plot line up above is our median age model for O18 alignment only, and the blue is our multi-proxy. And so what you can see is that those radiocarbon dates in black there have shifted our estimated ages over the Holocene compared to O18 only alignment. And so we've gotten some improvement in the accuracy of the age model that way compared to O18 only. If we compare the multi-proxy to the radiocarbon dates, well, first of all, the radiocarbon dates don't go all the way through the Holocene. So if we were doing C14 only, we wouldn't really have any information at all beyond since 10,000 years. So our multi-proxy is allowing us to estimate the ages better past the end of the radiocarbon dates. But also, if we look at the older part of the core, there's a 10,000 year gap between the last radiocarbon date and the next to last. And so that gives us larger uncertainties when we're looking at C14 only age models. But there are a few O18 data points within that gap that can help guide what the age estimates should be between those two dates. And so if we compare the uncertainty of the radiocarbon only, which is in orange, with the multiproxy in blue, we have a reduction of about 2,000 years in the 95% confidence interval when we do a multiproxy age model compared to a C14 only. So this is just one example of how multiproxy age models can improve the accuracy and reduce the uncertainty of aligning a single core to a target record. In addition to the two components that I've talked about so far, now I want to talk about the stacking. And so this is a really powerful feature of BIGMACS as well, is that it can generate stacks of data in an automated way. So it's a lot less labor intensive than traditional methods of creating stacks. It requires fewer cores than traditional techniques for making stacks. And it's taking advantage of this multiproxy technique to give us integrated age information from both radiocarbon and O18 alignment. So first, I just want to talk about the general way in which stacks are created and some of the variation between different stacks. So one thing that all stacks share in common is you have to choose what cores you're going to include in your stack. And typically you want to find a set of cores where you think the change is the same or very similar between those cores, and it's changing synchronously in time. Now, depending on the scale that you're looking at, you might not worry about shifts of 1,000 years because you're looking at something global, or you might want to look specifically at a region where you want to be very precise about the similarity between those records. The next thing you have to do is the cores have to all be on an age model in order to create a stack. So there's some choices that you can make about how you constrain the ages before you do the stacking. One is you might not do any alignment of the records at all. You might just use radiocarbon dates or original publication. That's going to give you a lot of signal degradation typically if you don't do any kind of alignment step. You could do minimal alignments where you pick a small number of tie points like termination midpoints in creating your stack. Or you can do this full signal alignment to a target where you choose one particular target and you align all of your cores to that target. That's going to be somewhat sensitive to the choice of the alignment technique that you do. And then the third thing that you have to do for stacking is find some way to combine or average the data between cores. So some stacks are actually principal component analysis or EOF analysis, and those typically interpolate each of the records evenly in time. Another technique is to divide the time span into bins of say 1,000 years and just average all of the individual O18 values within each 1 kiloyear time bin. And then this BIGMACS approach is something different. It's a time continuous estimate of the O18 values through time using Gaussian process regression. So I'm going to go through those 3 different techniques of interpolation, binning, and the continuous Gaussian process regression in more detail now. So first, let's compare the interpolation versus binning and talk about some of the differences between those techniques. So in interpolation, if you're getting a value estimate for each of the cores at every point in time. So all of the records are equally weighted. Whereas in binning, you're looking at the individual measurements from each core. So high resolution records are more represented than low resolution records. And the advantages or disadvantages of that depends on how you want to interpret your stack. If we look at interpolation, it's more typically used when you have a small number of cores because you want to make sure that you include information from each core at each time point because you don't have that many total cores. And it's been used for lots of different studies. So here's just a few examples, the Hybers and Wunsch Benthic O18 stack from 2004. Actually, it's a Benthic and planktonic. What you're looking here is the first principal component of the 6th highest resolution planktonic and 6th highest resolution benthic. And they did minimal tuning. So those black dots are the alignment points that they used for that record. The study of Clark et al. In 2012, where they were looking at sea surface temperatures, they did interpolation and principal component analysis for each region globally. So you're looking at, in blue there, the first principal component of the South Pacific SST, which had 8 different records included. And then in the bottom is a sea level stack done by Spratt and Lisiecki, where the short stack had 7 records and the long stack had 5 records. Now, the reason why we had to do those 2 different stacks is that in order to do this principal component analysis, the records have to span the entire length of the stack. So we have a shorter record that has more records and then a longer stack that has fewer records, so that we can accommodate different length records in that analysis. Interpolation technique is going to be sensitive to the resolution of the data. If you include lower resolution cores, you're going to have some signal loss because you're interpolating between widely spaced data. And then, so let's contrast that with binning, where high resolution records are weighted more heavily. This technique is relatively resilient to cores starting and ending at different points in the stack. So that's one advantage. So for example, in the LRO4 stack, there's a lot of records in the late Pleistocene and very few records that go back to the Pliocene. And so we used binning in that. And we included records with lower time resolution because they did not cause very much signal degradation because they just don't add that many total points. You do need to balance your bin size to make sure you have enough measurements within each bin. So as you have lower resolution data or fewer cores, you can compensate for that by having larger bin sizes. So in the LRO4 stack, for the late Pleistocene, we have a 1 kiloyear bin size, and we've got about 30 points per interval. Whereas at the Pliocene, we increase our bin size to 5 kiloyears because there are fewer records, and we have 15 data points per interval on average in the Pliocene. And so that's going to affect the statistics of the error bars on your O18 values, depending on the number of data points in each interval. So another example from Stern and Lisiecki, 2014, we made regional stacks, and different regions had different number of records. So the deep North Atlantic had 94 different records included. So there's a lot of data available for that. And we used 500-year bins for the deep North Atlantic. For other regions, we had less data. So the light blue there is the intermediate South Atlantic, where we had only 8 records. And we used an interval bin of 1 kiloyears. And even so, we had often fewer than 10 points per data point in the stack. And so that produces larger standard errors, so more uncertainty on the O18 value when you have fewer data points in each bin. All right, so let's compare that to what BIGMACS does. So as I said, it's an automated process. So you just start the software and it runs for a couple hours, a few hours, and then you get a stack out. And so this allows you to experiment more with different sets of cores and how that affects your results. The way it does the stacking is it iterates between an alignment step and a stacking step. So it'll do an alignment, estimate a stack, and then do another alignment to the new estimated stack. So instead of choosing a single target, you're iteratively solving for the target. So that makes it less sensitive to what you start out with for your initial guess of what you want to align to. And then it's also incorporating those radiocarbon ages during the stack construction process. So the averaging technique that we use to create the stack is Gaussian process regression, which is also known as kriging. It allows us to estimate in a time continuous way what the O18 value is throughout the core, using weightings of the neighboring data points. We use, you choose what kind of kernel you want to use. And so here we're using the Ornstein-Uhlenbeck kernel. And the width and the shape of that kernel are set by hyperparameters that the software solves for based on the kind of data that you have. One advantage of this technique is it will generate larger uncertainty estimates where the data are sparse. And so what that means is that you can create a stack with fewer cores, as it's okay if there's some areas where there are the data is less dense, you'll just get larger uncertainty intervals in that part of the core, in that part of the stack. The stack uncertainty does also include alignment uncertainty. So that's different than the traditional stacking techniques where the alignment is done first and then you estimate a stack. And the output gives you a time continuous O18 stack. So you will get an estimate of a mean and a standard deviation of O18 values for any time you want within that stack, instead of interpolating between a fixed resolution in the stack. So here, I want to give you a couple examples of stacks that we've created using BIGMACS. And what we've done is we've targeted these to be quite local or small regions, because we can create these stacks with fewer cores. So this is a mid-depth Northeast Atlantic stack. So you've got 3 cores from the Iberian margin and 3 cores from off of West Africa. They range in depth from about 2,300 meters to 3,200 meters. We picked these locations based on estimates of the water composition at these locations. So at the present day, these are between 80 and 75% North Atlantic deep water. It's just below the core of the NADW. And we've also looked at reconstructions of water mass composition for the LGM. And we believe that these also have very similar water mass compositions at these locations during the LGM as well. So we think that they are changing synchronously through time, occupied by very similar water mass compositions. This is what the stack looks like. So we have a high density of data points all through the deglaciation and the second half of MIS3, and then fewer cores as you go further back in time. For stage 4 and older, we have 2 and then only 1 core for stage 5E. And the software is able to handle that. So you can see that in places where the data are very sparse or there's a bit of a gap, the data is interpolated across that with reasonable error bar estimates. So for example, when the data end, the uncertainty gets larger at the end of the stack. If we compare the O18 values estimated for this stack with a deep North Atlantic stack that contained 94 cores from Lisiecki and Stern in 2016. So this was all cores from the North Atlantic deeper than 2,000 meters for that deep North Atlantic stack, compared to a very targeted region with 6 records for the mid-depth Northeast Atlantic stack. And one thing that you can see that stands out right away is that you've got smaller error bars for this more localized stack. And I think it's because you have a more consistent water mass composition across those sites, so a stronger similarity in signals. The data are also smoother because of this Gaussian process regression. So we're boosting the signal to noise amplitude by performing this Gaussian process regression. However, even though we're doing some smoothing, we're still preserving, in most cases, the millennial scale variability in those data. So what you can see is that during the Heinrich events of stage 6 and the millennial variability at the end of stage 5, we still have the localized blue curve passing through, showing similar variability. Although I would probably not use it to estimate the rates of change during these events, because it could be some, the smoothing could impact the estimated rate of change for some of those events. because we're doing multi-proxy ages, we've got this simultaneous iterative alignment that incorporates all the age constraints. So for the 6 cores that we have a total of 150 radiocarbon dates between 0 and 50,000 years ago. And we're taking advantage of all of those age constraints in the age model. You can also include other kinds of age constraints. So the purple crosses there are tie points between the SST in MD 952042 with a Speliothem age model for millennial variability. And when we run that, we can compare the multi-proxy age estimates for each of those individual cores with their radiocarbon only ages. So here 0 would be that the multi-proxy age matches exactly with the radiocarbon only age, and the radiocarbon dates of course have uncertainty, so we don't expect that to be exactly 0, but you see that we have just very small shifts between the radiocarbon only ages and the multi-proxy ages. So all of those radiocarbon dates are consistent with each other and the O18 alignment. Here's another example stack. So the mid-depth Northeast Atlantic stack is sort of our ideal case of very high resolution data with a lot of signal to align. So now we're going to look at a case of some slightly less well-behaved cores. So we're looking at, we've created an intermediate tropical West Atlantic stack. So we've got 4 cores that are on the boundary between the Antarctic intermediate water and the North Atlantic deep water. So they're about 50 to 70% NADW in the present day. And this is what we've got 4 cores. This is what they look like. So the O18 data is quite noisy. There's a lot of outliers, possibly from material moving down slope. And those are our radiocarbon dates in the triangles at the bottom. And so despite the fact that these data are noisy, we're still able to produce a stack, and we've got confidence intervals, O18 error bars that reflect the amount of scatter in the data. And this is then just a comparison between the deep Northeast Atlantic stack and the intermediate tropical West Atlantic stack. So we can see the mean offset in the O18 as well as the wider error bars, and the general smoother nature of the tropical West Atlantic stack mostly relates to the fact that it's got less data. And so we have more uncertainty, lower resolution. And so in summary, the advantage of our new BIGMACS multi-proxy software is that you can create age models without any parameter tuning. The uncertainties are based on a physical estimate of sedimentation rate variability in ocean sediment cores. It's a multi-proxy approach, so it's using direct age estimates as well as O18 alignment that's producing smaller age uncertainties. And we have this automated local stacking. So instead of having to take a lot of cores over a larger region to create a stack, we can look at very specific areas of the ocean. And then we're getting really good age control by being able to use the radiocarbon dates from all of those cores in the local stack. Some of the limitations of BIGMACS is it is quite computationally expensive, but the runtime is not prohibitive. So to create a multi-proxy age model for 1 core aligned to a target only takes a minute or 2. To create these stacks that you've seen takes an hour or 2. So again, not so bad. We have done some longer stacks. So an 800,000 year late Pleistocene stack could take 6 to 12 hours though on a desktop machine. So if you want to do longer stacks, then it starts to be a little bit more time consuming. As with all stacking techniques, you need to assume that the Benthic O18 change is synchronous between the sites that you're analyzing, either for creating a stack or for doing the multi-proxy alignment. So you want to have some information that tells you that the sites that you're analyzing together are reflecting similar water mass compositions through time. And then in terms of the timescales for which BIGMACS is appropriate, Because of the smoothing we get from the Gaussian process regression, I would be hesitant to interpret the details of anything that's shorter than a kiloyear. So to look at really abrupt change could be something you probably wouldn't want to do with one of these BIGMACS records. And then, as I said, we've calculated stacks up to 1 million years long for the late Pleistocene, but we haven't really done testing on anything longer than that. And so probably for anything longer than that, BIGMACS is not yet suitable for doing that, something we're working on now. And so, like I said, we're hoping to submit this to Climate of the Past within the next couple of weeks. So if you want to learn more, you'll be able to look at the details there. But I'm also happy to answer any questions you have now. Thank you.
Okay, thank you very much, Lorraine, for the very informative talk. And I think the tool will be very useful for many people in the community. So are there any questions for Lorraine? Oh yeah, there are people. Marco, yeah, you can directly unmute yourself.
Okay, perfect. Oh, thank you so much for the talk. It's very interesting. It sounds like it's going to be very, very useful. I do have a question regarding the Bayesian part of the model. So you did mention that you have a couple of parameters. One of them was a memory parameter. What kind of priors are you using for those parameters?
Yeah, so those are all fixed. Well, so we start out with a model based on the data, and then based from those 37 radiocarbon dated cores. But you can either run it with that sedimentation rate model fixed to stay the same as that, or you can allow it to adjust the hyperparameters based on the data that you're analyzing. The actual components of that model are this histogram of sedimentation rate frequency, and then also we've calculated the frequency at which the sedimentation rates change from either being above average, average, or below average. So the transition probabilities between those three states. And again, you can either just keep it fixed based on the data that was used for training, or you can allow it to adjust as it runs to tune those hyperparameters based on the data that you're actually analyzing. So you don't set any of those numbers. They all are either using the training data or adjusting within the software.
Okay, so it is not really like a defined prior distribution that you can later change. It is already trained.
No, the idea is that you don't set it. It's set for you.
Okay, well, that goes to my next question, because usually when we work with Bayesian models, what you have to do is actually do some sort of robust testing where you actually move the prior distributions as much as you can to see if you remain consistent in the results. So was there any sort of test like this done in this model? Yeah,
so we've done extensive testing of small adjustments to this, and it's fairly robust with respect to small changes in this underlying model.
For example, if I have a new set of cores where I have these sedimentation rates, like similar to this training data you're showing right now, is it possible for me to actually come to the software and put that training data in and the model will learn that, or will still be using this one that you're showing?
We don't yet have it set up easily to change that, but obviously you could go into the code and make your own and put in your own model, and possibly in a future version we might have a pro version of the software where we allow more options for people who are interested in really developing the tool rather than just using the tool.
Okay, thank you very much.
Okay, I think Nikita has a question. You can directly ask. Yeah.
Hey, thanks, Lorraine. It was really good to listen to the talk. I work on stalagmites, and we've been wondering how to do something similar, but with stalagmites only. And I was wondering how transferable the similar method would be to a different archive. So, for example, could you align to an oxygen isotopic record that was from a stalagmite from a region that was particularly high resolution and really good instead of the Benthic curve? Would it translate, or it just wouldn't work given different sedimentation
you're talking
rates?
about whether you could align two stalagmite records to one another. Is that what you're asking?
Exactly.
Well, I think you would definitely need a different underlying model of accumulation rate change because the process is so different there. And I mean, you have a lot of advantages in that there's no bioturbation, there's no movement of material down core in a speleothem. I think the overall framework would work. I don't think you could just take the software package as it is to run it that way. Yeah.
Okay. Sounds good. Thanks. That already answers my second question. Thanks, Lorraine.
Okay. Maybe before. Okay. There's one more. Yeah, please, Francisco.
Hi, Lorraine. Hi. Thanks for the great talk. I'm a really big fan of your work. I was wondering, going back to the training data, so the histogram of sed rates, something that I was wondering is if you can tell us a little bit more about the radiocarbon measurements that feed into these training data set, and whether that distribution is somewhat affected by changes in marine reservoir correction, and how that would affect down the line the alignment that one would generate.
Yeah, so the description of the training data is all in this Lin et al. 2014 paper. It uses a pretty I think it uses the 2013 version of the reservoir age estimates, and so and calibration curve. And so if you updated it for a different reservoir age change, it would have a small effect. I don't think it would be an enormous effect because we're looking at like 4 orders of magnitude here in sedimentation rate changes across that histogram. So I don't think it would be very strongly affected by small changes in reservoir ages or the calibration curve.
I guess these are not cores from polar regions, right?
No, this excludes anything north of 40 degrees. It's because we were trying to avoid the reservoir age changes.
Okay, so if I may, just a very quick follow-up question. So, and I guess if we're using 14C as a tool for synchronization across cores, that another assumption that goes into the model is that the local reservoir is pretty much the same, right?
Do you mean for the training data or when you're actually creating your age model?
No, when you're actually creating,
when you're creating the age model, you specify what calibration curve and reservoir ages you want to use. So that's something that you decide what values you want to use for calibrating your carbon data. Great question. I should have clarified the talk.
Thank you.
Yeah, I actually had a very similar question to Francisco. So, but I want to add maybe more thing to what he asked. So is there, or will there be a chance to add in something like the system can determine the reservoir age for you instead of, everyone has their own reservoir age choices?
It'll come with some built-in options, but it's not gonna, at this point, it doesn't take a latitude and longitude of your cores and give you a reservoir age estimate. That's something that you have to supply an estimate of the mean reservoir age for your site.
Yeah, okay, I see. Thanks, Lorraine. Are there any other questions? If not, then let's thank Lorraine again. Thank you for the very nice talk. And for the next talk, I think we will not have a talk for August. We will have a summer break, and then we will resume in September. So please stay tuned for the advertisement for the next talk. And towards the end, I would like to thank Lorraine again for the very nice talk, and we hope to see you next time. Okay, thank you very much.
Thanks.
Thanks, Lorraine. See you. Take care.
Bye.
Bye.